In this case, we were examining silver silicon multi-layer. So you have silver and silicon stacked over each other. It turns out that the lower layers of the cake were completely degraded. So we had 5 layers at the beginning, right? And now 5 bilayers at the beginning, and now we only have 3.
There are quite a lot of things you have done. You have been in quite a lot of labs. And my next question might be a bit difficult, but I'm still going to ask it. Do you have a research project out of all the different kinds of experiments and research work that you've done so far? Do you have one research experiment that you're super proud of? And if you do, I hope you do, could you explain it to us in simple words in the section we call In Other Words?
Yes. Well, I'm going to choose the latest publication that got published because that's the thing you are the most proud, right? I'm still in the rush. I mean, it got published, it got accepted a while ago, but it got published 3 days ago from the moment we're recording this podcast. So I'm allowed to choose it, I guess.
Congratulations. Yes, of course you're allowed to choose.
Just because of that. Yeah, well, that's the idea. It's closely related to what we were talking about. Right. In this case, we were examining silver silicon multi-layer. So you have silver and silicon stacked over each other with sizes varying from 15 to 28 nanometers, if I recall correctly. And
what do you have?
So we had 5 bilayers. So we actually also played with that at some point in the paper. But we have 5 and 3 bilayers, so 10 and 6 layers in total, with a repetition unit varying from 30 to 40 nanometers. So yes.
Okay, alrighty. So very thick.
For
nano scale, very thick.
Well, overall it's very thick, right? But then we had silver layers of 12 nanometers. They did not get to the paper, but we also synthesized 4 nanometers thick silver layers using this. And yeah, we designed them as a metamaterial to be a super absorber, the near perfect absorption, meaning that less than 1% of the light that goes in gets reflected or transmitted. We designed them for that. And well, first of all, optically, like as we're saying, in my lab, we try to do things that are scalable, right? These multi-layers, I was sputtering them in about 1 hour, while typically these metamaterials take days to be fabricated. However, there's a problem coming with this, and it's that the interface between the 2 layers is not going to be super smooth if you do it so quickly. But actually, we found out it's something that we had already been researched in literature, but we confirmed that actually this disorder that happens of it not being super smooth, it's actually beneficial for the application. So it actually improves the absorptivity of the whole thing. So disorder is not necessarily bad, okay? That's the first thing, and it's actually good. And then we just decided to study what was the maximum temperature at which this behavior would be found. And then what we found was actually very surprising, because there was a temperature range at which the optical properties were still the same, but if you actually did a FIB cross-section, so FIB is a focus ion beam, it means we send ions to cut it, and then you actually look at this cut that you did with
it's like cutting a cake, and FIB is like the knife.
Exactly that. You cut a cake, and if you look at the layer structure in the cake, it turns out that the lower layers of the cake were completely degraded. So we had 5 layers at the beginning, right? And now 5 bilayers at the beginning, and now we only have 3 because the further down 4 layers were completely intermixed. But one would never say that looking at the optical properties, because once it's the optical properties and they are the same, and we ran a lot of tests about that.
Right.
And that sparked the question. First of all, why is the degradation starting down? Because if you look at literature, typically it's assumed to be isotropic.
At the top, yeah.
At the top or somewhere or quite regular through the section, right? And secondly, how can it be that the degradation doesn't impact actually the optical properties?
Right.
And this is what we researched. we tried to find using also simulations, and then that's the thing I'm the proudest about. We did tomographies, so it means, imagine, we're taking a picture of the SEM scan we're just taking a picture of the cake. We're cutting a bit more, and we're taking another picture, like to see whether this is something that just happened at this depth or if it's actually. And this allowed us to get tomographies that then we could simulate on. So we could do 3D simulations. And this way we found out that this was driven actually by stress.